Hello. Hey. Okay, so the Maths Union is running a LaTeX workshop tomorrow. So if you don't know what LaTeX is, it's a typesetting thing, typesetting language which you can use to make all your maths reports and stuff look absolutely beautiful. So that's like, it's upping your game from Microsoft Word to LaTeX. So that's tomorrow, 12 p.m. to 2 p.m. in the Web Lecture Theatre. It does clash with this lecture tomorrow, so just, I don't know, choose. But there'll be free pizza midway through, and yeah, if you want to make, and it's also the expected typesetting software for your honors and PhD theses. So I mean, if you're planning on doing that, definitely something to get onto, or if you're just interested in making beautiful maths on the computer, something to look into. Okay, so if you want to take a photo of that for that info, but otherwise, yeah.
What distribution do you use? Do you do it on Windows or Unix or Mac?
I guess I think all of the above. I don't know.
What editor? Do you know what editor they're using to teach it?
No.
Okay.
I think maybe just, I don't know exactly what editor
Okay.
they're using.
No, that's all right.
I'm very like, I don't know much about that.
Oh, right.
So that's why I'm very keen to get
Oh, no problem. Right, so if that didn't make any sense to you, so LaTeX is what, so most mathematicians don't use Microsoft Word, because anyone ever used equation editor in Microsoft Word? It sucks, doesn't it? Yes? Right, it's awful, right? So LaTeX is what your textbooks are written in, right? And the beauty of LaTeX is it's free. It doesn't cost anything. The downside is that LaTeX is not what we call a WYSIWYG program. So it's not a what you see is what you get. But so for example, just to show you, everything I give you for this unit, is written in LaTeX. So this is on a Mac, this is what it looks like. Oh, you can't even see. Right, and the good thing is that we don't have to use Microsoft Word. And so I type what's on the left, and it renders what's on the right. And maths looks much nicer. And it looks a lot more complicated than it actually is. Right? So basically I just write here, and we call LaTeX it, and then it produces a PDF that looks like on the right. Right? But it's free and open source, and if you're a scientist or an engineer, writing maths in LaTeX is so much easier than doing it in Word. Right? And as I say, it's free and open source, and you can use it on any machine, Windows, Mac, Linux, it makes no difference. So if you can go, although it clashes with this lecture, it is a very handy thing to learn. So if you want to create beautiful documents, LaTeX is the way to do it. Right? As I say, it's what all your textbooks are written in. It's pretty cool. So, but there is a bit of as you can see of the commands on the left, it is a bit of a learning curve, but it's actually not as bad as it looks. So anyway, so that's a good thing. I didn't know the union did that, so that's good. Anyway, let's get this link going, see if it's working. I'll be right back. I've just got to check next door, see if it's working. Right. Okay. All right, so let's get going. First things first. So your first class test has been marked, and the way it'll work is I've separated them all in terms of if you ticked your practical class, as long as you tick the right one, you'll get them back in the practical classes this week. If you forgot to pick your practical class, tick the front of it, they're with me, right? So you'll have to come to my office during my consultation time on Wednesday to grab them. All right, now if your mark is up on CS marks but you don't get it back during your practical, come and see me, right? Most likely it's been mixed up somewhere. This is a big class. As long as your mark is on CS marks, the paper is somewhere, right? And by the end of the week when I get them all back, we'll find it. If your mark is not on CS marks, now I've had one person email me to say it's not, most likely what happens in that, my marker has just missed your paper, entering your paper. Don't panic at this stage, right? Come and see me and we'll hunt it down. Yes? Did you email me? Are you the person that so your mark's not on CS marks and nor is yours? Oh crap, that's 3. Right, don't panic, it'll be somewhere, right? So if you get your test paper back during your practical, you've got to show it to me so I can record the mark. If you don't get it back, come and see me in my office and we'll hunt it down. Okay? Don't panic at this stage. Yeah, you know what happens, the staple papers stick together and, these things happen. Don't panic at this stage, okay? But other than that, everyone did pretty well, so average was good. So I've uploaded solutions as well. You'll notice I was a little bit lazy. You might have noticed if you've already had a look, I was a bit lazy with version A and version B, right? So, I mean, version A, for example, this question was sine squared plus 1 on 2 plus x. I think version B was 1 plus sine squared on x plus 2. All right? So the solutions are for both. Yeah? So if you believe your marking is wrong, my markers do make mistakes. I do give them a marking key, but they can misinterpret it or miss it. Don't worry, you can show it to me and I can look at it. If you think that you've been marked wrong or they haven't added the marks up or some rubbish like that, just show it to me and I'll have a look and I'll fix it if necessary. Okay? All right, so yeah, that's all up there. Also, I've uploaded your next so-and-so assessment. Now, obviously, we've got a mid-semester break, so it's not due this Sunday, it's due next Sunday, right? So, and it's 5 questions as normal. Right, but it's not, it's not due for 2 weeks from yesterday instead of this Sunday, okay? And of course, Good Friday is a public holiday, but that doesn't affect us. Like, we don't have any classes on Friday, do we? Are there any practical classes on Friday? I should know. There's 16 of them, right? I don't think so. Anyway, right, Friday's a public holiday, of course. So, and being the Easter long weekend, I didn't want to make it due this weekend, so it's due next weekend. It's just 5 questions as normal, okay? All right, yeah, but do make sure you attend the practical classes and get your test back. But if you don't get your paper back, either you've not marked the practical class or it's just been misplaced, okay? So don't stress. As long as your marks on CS marks, your paper will be there somewhere. You just got to find it. Okay, now, what we're going to do this week is just do one last thing with integration, a topic I don't like, right? So you remember when you did differentiate, when you first learned differentiation, you would have probably had a question where you would have spent the first lecture or class or whatever the hell doing derivatives from first principles, yeah? So you would have remembered you have to do this sort of thing where we know that formally the definition of a derivative, there's different ways to do it, but they're all obviously equivalent. Right? It's a limit. Yeah? And you can show what the derivative of x squared, for example, would be, you clean this up, you get, what do you get? You get all these have limits, of course. And limit as h goes to 0, that's, you know. And you spend all this time doing this, and then the next lecture you'll say, actually, we never do it this way. Right? And you think, what the, you know. Right? So you don't go to first principles unless you really have to. And the only time we'd have to nowadays is really weird functions that you're not going to see for years. Right? I mean, in third year maths, you might start doing some very odd, if you do a math degree, you might start doing some very strange functions that aren't, we call them generalised functions. They're very weird, right? Because they don't follow the normal rules. But, you know, those sort of cases, yeah, you have to go to first principles. But for this sort of, you know, just product quotient chain rule, table of derivatives, off you go. Integration's the same. You can do integration from first principles, right? So unlike derivatives, which are like a limit, basically integrals, remember when integration was first looked at, it was basically answering this question: how could I find the area under a curve? Now, if you didn't know the first thing about calculus and that integration was the opposite of differentiation, well, how would you do it? Well, you'd use what you know, right? You'd probably approximate that area by rectangles, wouldn't you? Right? You'd take this thing and you'd you'd probably do something like this, right? So you'd find rectangle. Of course, we can all find the area of a rectangle, base times height, right? Let's, for the moment, keep life easy and assume that they're all the same width, right? So the x0, x1, we've equally partitioned between x0 and x5 up into slices. The height, we pick it either where one of the corners hits the function. You could have it where the first corner is hit, so it underestimates the area. So obviously this one, if you sum all the area of all these rectangles, that area is going to be less than the actual area you want. Right? That's called a lower Riemann sum. Right? Now you could also do it where, you know, instead you'd have this rectangle up here, so they're all overestimated, and then you get bounds. So the area is somewhere between this and this. And you can imagine if you use more and more and more slices, so thinner slices, the answer gets better and better and better. You know? In the limit that the thickness goes to 0, that is the integral. Right? So basically, we're approximating a definite integral here as a sum of areas of rectangles. Right? Makes sense, doesn't it? Yeah? Now, in the limit as the width of the rectangles goes to 0, we have to sum infinitely many of them, and that's called an infinite series, which is something you'll learn about in Math 101 too. Right? How we can sum infinite series. Right? And that's what that integral sign looks like an elongated S, doesn't it? It looks like an S that's S for sum, because that's what you're doing. That's what an integral is, a sum of areas. That's actually what it does. And you can do all these problems from first principles. So, for example, in the unit reader is this problem. So this is in the reader. All right, let's say we've got to integrate x from x equals 0 to x equals 1. Right? So a definite integral, right? So integrate x from 0 to 1. Now, of course, we know how to do that. It's a half x squared evaluated at 1 minus a half x. Yeah, so it's a half, right? It's also basically an area of a triangle, right? Half times base times height. But if you want to do it from first principles, you partition the thing, you know, into n partitions, right? So you take n slices and work out what the sum is of all the areas, and you get this finite sum up to n. Right? And then you need things like induction or things like that. We've probably all seen the classic thing that the sum of the first n integers is a half times n plus 1. You've probably seen that at some stage. Everyone does, at specialist level, you all do induction at school. Right? Interesting story who came up with that first. So the story goes, there was a famous mathematician hundreds of years ago called Gauss. So if you go and you start doing complex function theory, you'll hear his name a lot. He did a lot of amazing work. Gauss was a genius. And he was one of these child geniuses, right? And so the story goes, I have no idea if it's true, but the story goes that the teachers teaching primary school back in 1600 and whatever the hell it was, obviously needed a break and gave them a task and said to the class, all right, you got now go off and sum the first 100 integers. And thought, yeah, that'll keep them busy for a while and shut them up. Right? And Gauss did it in under a minute. Right? And the teacher didn't believe him, of course, so went home and did it by hand and got the same answer as Gauss. So next day asked Gauss how he did it. And Gauss said, well, it's easy. That's all, maths is always like, oh, it's easy when you see the answer. Right? But basically you've probably seen this before, but basically what Gauss did, basically was asked to calculate that. 1 plus 2 plus 3 plus 4 plus 5, So let's call that S. Right? Now, of course, the order you add them up makes no difference, does it? Right? That's the same S, isn't it? Now, if I add these two, you'll notice you'll get right, so 2S is 100 times 101, so you're adding up 101 100 times, right? So that's where the classic formula, sum of the first n integers, half times n plus 1, that's where it comes from, right? So if you use that result, right, you got this sum, take the sum, take the limit as n goes to 0, right, because the n is the width, you do it. Right? And so if you pick up a textbook on calculus, they'll spend the first part of the integration chapter doing it from first principles, only in the next lecture to turn around and say, actually, we don't do it that way. Right? So I don't like it either. So all you have to understand is the simple idea that you could do integration from first principles by slicing it up into thin rectangles. That's all I want you to take out of this. And I am never, ever going to get you to do this from first principles. In my opinion, it's a complete waste of time. The only time you would do this is with functions that you can't integrate, right, or that are weird. Right? And actually, there are far better ways to do it. The best way to do an integral you can't do, because remember, integration can't always be done, the best way to do it is Taylor series. Now, we did Taylor polynomials. You'll do Taylor series in Math 101 too, because that will always work, because every Taylor series involves differentiation, and you can always differentiate. Right? So, yeah, we don't normally do it this way, unless the function we're doing is very weird. Right? But essentially, this is what we call Riemann integration. Right? And it's basically just slicing this thing up into partitions. There's some terminology and stuff. Right? We ain't going to do it. All you need to take into account is that this simple idea. You sum, take small pieces and sum them together. In the limit that the small pieces go infinitely small, that's an integral. That's all you need to worry about. Right? And we can use this idea to calculate all sorts of things beyond areas under curves. So we can calculate things like volumes of revolutions, and we're going to do volumes of revolutions and what's the other one we do? Lengths of curves, but you can do it to calculate the concept of an average of a function. You can do all sorts of things with this idea. And in physics and things like that, you can calculate things like work. So you remember work is force times displacement, and force being the first derivative of velocity. Second, you can do a work as an integral. In physics they call them line integrals or path integrals. We're going to do those in a few weeks. But anyway, all right, but that's basically the idea. So the idea is you slice it up into slices and sum them. Right? Although I'm never going to get you to do that, ever. Right? What's more important is the idea behind it. Right? Now, you can use this idea to prove all of the results from calculus we're familiar with. That integration is indeed the opposite of differentiation. It's all in the unit reader if you're interested, but I'm not going to assess it. Right? So I'm an applied mathematician. I care about doing the damn integral, not worrying about, its properties. I know its properties. Right? So I don't need to reprove them. So anyway, it's in the unit reader if you're interested. But we can use this idea to calculate two things we're going to do, which is volumes by revolution, which you've probably done before, and length of curves, which you may not have seen before. Right, so let's say we've got some volume of revolution. So basically what we're doing is we've got some function of a single variable and we rotate it about one of the axes. And I want to know, how do I calculate the volume? Well, what we do is we find the area of lots of little slices and sum them. That's what the integral does. The integral is like a sum of lots of little pieces. Right? That's the only, idea you need to take away from, Riemann integration. Right? Right, so let's say we've got some solid in space, and suppose the cross-sectional area, we know what the cross-section area is. It'll be a function of something, right? And all we do is we just sum all the slices up. We find an expression for the area of an individual slice, and we just sum them all, which is what the integral does for us, right? So we just partition this thing, right? And in the limit, as the partitions go small, the volume is the integral of all of the areas. So think of this, this makes sense. The volume is the sum of all the area slices. So imagine you've got like, I don't know, a cup, right? Take lots of little slices that are really thin. You can calculate their areas, right? We know how to calculate the area of a ring, pi r squared, yeah? Right? So you take slice them all up, calculate their area, and then sum them. Right, which in this terminology is the same as integrating them, right? Because the integral is like an infinite sum. Right? That's all you need to worry about. So all we need to do here is find an expression for the slices of the area, because their volumes of revolution, they're always going to be, so they're always rings, basically, annuli or whatever you want to call them, discs, right? Whatever you want to call them, circles, whatever. Right? So as an example, let's say I want to know the volume. I've got this function y equals x to the third, which is the blue part. Imagine I rotate that about the x-axis, right? So it forms a, I don't know, a teacup without a handle on its side, or like a, I don't know, whatever, shot glass, whatever you want to call it, right? Some sort of cup thing, and you want the volume. Well, I can figure out, if I do vertical slices, and I calculate the area of all those slices, right, the area would just be pi r squared, wouldn't it? Right, and the radius of any slice is just this distance, isn't it? Right, the value of the function, basically. Right, so the area of an individual slice is just pi times x to the third all squared, pi r squared. Yeah, and then you do the integral to sum them all. Right, so a slice here. Would have, let's say that's a half. So the slice here is a half to the third all squared. That's its radius times pi, right? And you just sum all the slices. You imagine slicing this thing up and then summing them all, yeah? All right, so we need an expression for the area, which is just pi r squared, the radius coming from the value of the function. And then you read this as the volume is the sum of all these slices from 0 to 1, right? Because that's what the integral is, like a sum. Yeah? Right, so all you've got to integrate is pi r squared, so it's the function's x to the third, so x to the third all squared is x to the 2/3, done. Right, and that's where the idea comes from. What if I rotated that thing, that blue curve, around the y-axis? Right? Then what I'd have is slices where the integral is with respect to y. Right? Because in that case I'd integrate from y from 0 to 1, but the radius expression I need to solve that for x, that's x equals y cubed. Yeah? So I'd integrate pi times y cubed all squared from y from 0 to 1. Right? And I take horizontal slices. So it depends on the question. But it's always pi r squared. All you've got to do is figure out what an expression for r is. Right? So you take note of which way I'm asking you to do the revolution. Right? And formally, some textbooks would get you to set up the Riemann sum. The idea is simple, isn't it? Right? You just take slices, integrals like a sum. You just sum them all. Right? Now, there's a couple of examples in here. So here's a good one. So we'll revisit this concept a lot, but all of the area and volume formulas you learned back in wherever. So what's this one? The volume, we should know, hopefully, the volume of a sphere is given, so a sphere of radius r, the volume is 4/3 pi r cubed. Yeah, we all know that. Prove it. Right? Where does it come from? Right? Almost every area or volume formula you're used to, like pyramids, whatever the hell it is, they all are formally defined as integrals, because that's what integrals give you. Areas or volumes or lengths or these sort of, depending on what you're doing, they all actually formally derive from defining the thing as an integral. And the hope is that you can do the integral. That's actually where this all comes from. So if I want to prove this, let's say I don't know what the formula for the volume of a sphere is. Well, imagine I've got a semicircle, of radius r. Yeah? So I've got this function y is the positive square root. We know that the equation of a whole circle is x squared minus r squared. Remember, what I'm doing is I'm going to rotate this thing around the x-axis, say. Right? So if I look at just the top half, that's just the function, the positive square root of r squared minus x squared. Right? Now, if I'm going to rotate this thing around the x-axis, it's volumes of slices. So a particular slice is just pi r squared again, isn't it? Right? So it would be pi times this all squared at a particular value of x, wouldn't it? Right? And then you just integrate from minus r to r, and you sum them all. That's it. Right? So this one, right, you just got to integrate pi times r squared minus x squared. That's nice and easy to integrate, and lo and behold, that's where the formula comes from. Right? So we've actually proved it. Well, it'd be bad if we didn't. We've been using the wrong formula all our lives. Right? But that's actually where a lot of these volume things come from. Right? Let's say we've got this region bound by the curves y equals x cubed and y equals root x. And I imagine I'm rotating them around the x-axis, and I want the volume. Right? So you can imagine basically what I could do is I could do this two ways. I could find the volume of the upper part, root x, revolved. That'll give me a solid. Right? And then find the volume of x cubed and subtract them. Right? And outer volume minus, take the cup inside of the cup out so it's hollow. You see what I'm saying? Or you could do it in one hit. Right? So at a particular x, I take a particular slice. Look at my fantastic diagram of my slice. Right? So it's pi big R, this area. So the area of this thing with the whole donut thing with the hole in it is just this pi r squared minus this pi r squared. Right? So the top is root x, the bottom is x cubed. Right? You do the integral. Done. Now, because these are volume, of course, these have got to be positive. If you've got a negative answer, something's up, isn't it? Right? Volume can't be negative. Right? So either you've done the order wrong or you've done the actual integral wrong. Right? But you see, it's a simple idea. You just sum all the slices. Right? That's what Riemann integration is. Right? I just don't see the point of doing normal integrals from first principles. I just think it's a useless exercise, just like doing differentiation from first principles. Here's one that's not quite so obvious. Right? This is the amazing thing about integrals. So, like derivatives, differentiation gives us the rate of change. That's basically it. Right? That's all it's doing. Right? But integrals can give us all sorts of things. We can actually calculate all sorts of things by integrals because of this idea that it's like summing lots of little pieces. Right? It's a quick way to do the sum. And it all hinges on the fact that you can actually perform the integral, which is not a given. Right? It is in this unit, but in general it's not. Right? How would you calculate, how would you answer this problem? Let's say I've got some function, right? So this function y equals f of x, and I want its length. Right? So I'm not interested in its area or anything, I just want its length. Now the first thing you might think, well, this probably has nothing to do with integration. Integration's area, not length, but it does. Right? But how would I do it? Well, what you could do is you could partition it. If you want to get an idea of what's going on, you could break the curve up into little pieces, couldn't you? Right? And then that's what you're doing. You've got this curve, you slice it up and you find the length of all the pieces and then you sum them all together. Riemann integration. Yeah? So if I take a particular slice, say from one value of x, which I've called here x of j minus 1 to x of j, right, whatever that is, however I've decided to partition it, then I know the length between them is just their difference, isn't it? Xj minus xj minus 1. I know the difference in the height because I know the value. I know how to evaluate the function, right? So the difference in the height is the function at the bigger x value minus the value of the function at the smaller x value, right? And you might think, well, if the function's going down, that length is negative. I don't care, right? Because I'm about to apply Pythagoras, all the negatives will sort themselves out, right? Because I'm calculating a length. Now, if I want the length of the blue bit, which at this scale is not a particularly good approximation, is it? Right? You can see the black bit up high is a little bit longer, but you can imagine if this width between the x1s is small enough, it'll get better and better. In the limit that this width goes to 0, you're summing infinitely many of them, it will become exact. That's what the Riemann integral's doing. Right? So the first thing I do is I need to find an expression for this length, right? The hypotenuse. Well, good old right angle triangle, Pythagoras. The square root of the x bit squared plus the square root of the y bit squared. Now, there's a theorem that's in the unary called the mean value theorem. This is actually very straightforward if you draw a diagram. So the mean value theorem basically says this, right? It's a very simple idea. Let's say you've got some function between, say, x equals a right? We're assuming it's smooth, well behaved, it doesn't blow up, it doesn't do anything naughty, right? Right, so whatever the curve looks like. So this is just some function. Now, between these 2 points, so this is f at a, the value of the function at a. This is f at b. I can easily find the equation of that straight line, can't I? I know 2 points. Right? I can find the equation of that line, can't I? Easy. Yeah? But if the function's smooth and well behaved, somewhere between x equals a and x equals b, there'll be a tangent line that's parallel to the one this one that joins the points. It's got to be there somewhere, doesn't it? Right? You would think if the function's smooth and perfectly well behaved, somewhere in between x equals a and x equals b, say C, is somewhere where the tangent line to the curve will be parallel. They're meant to be parallel, right? But to that straight line. It's got to be there somewhere, doesn't it? Yeah? So that's basically what the mean value theorem tells you. So the mean value theorem says that somewhere there's a straight line, a tangent line that's parallel to the line that connects those 2 points. So somewhere there's the value of the derivative of the function, which is the slope, will equal the slope of that line between the 2 points. That's basically what this is saying. For some value c between a and b, or here xj minus 1 and xj. Makes sense, doesn't it? Yeah? Now, if I replace this bit in here with this, yeah? Right, you'll notice I'll get this squared plus this bit squared times this bit squared. Right? Now I can take that difference of the x value squared outside of the square root sign, right? And just take the positive square root because I'm interested in the length. So I could say that the length is approximately the square root of 1 plus the derivative of the function all squared evaluated somewhere times the width. And then the limit as the width goes small, this is a Riemann sum of this function. Right? So in other words, I can calculate the length of a curve y equals f of x by this formula. Provided the function is smooth and well behaved, everything we integrate is going to be smooth and well behaved. You can do integrals where the limits are where functions are misbehaved. They're called improper integrals. You'll do those in Math 101 too. We don't do them in this unit. Right? Right, so problem. As we've seen, we're bringing a square root in is not pleasant. Right? So a lot of the time these will be very nasty integrals to do. So there's tricks we can do this. Either, again, as always, I'm not going to give you one that's impossible. Right? So, and remember, with square roots, things get nasty. So let's have a look at this example. Define the length of the curve y is a third times x squared plus 2 to the 3 on 2 for x between 0 and 1. I basically plug everything into the formula, but I would recommend that what you do first is this. So we've got and this formula is on the formula sheet. You don't have to memorise this thing. The length of a curve between x equals a and x equals b is 1 plus its derivative. Right? So that's like you take lots of little lengths and you sum them all together. Now in this case we've got the function f of x right? What I would do the way I tackle these ones is because I know there's a square root in there and square roots are bad. Right? They usually will lead to nasty integrals. Remember, we've got ways to handle them now. Either the square root will magically disappear, they're the good ones, right? Or a simple substitution, or inverse trig substitution, right? We've actually, remember now, we have an integral method that we can handle these, right? If nothing else works. It's not pleasant, but we can do it. So, but what I would do first is hope I was kind and gave you one where the square root magically disappears. All right? So the first thing I would do, find the derivative of this. Again, if you don't do the chain rule in your head unless you're comfortable. All right? All right, so that's the derivative. Now I need this. Right, that's the bit that's under the square root sign that I have to integrate. Now the reason I calculate this first is I'll show you. So we've basically got... Why do I get the feeling something's wrong? What have I done? What have I done wrong? Oh dear! Right. Oh God, that's terrible. See, we all do it. That was a test. We all do it. Oh God, that's a terrible mistake. So this is actually... Three on two. Oh yeah, and I forgot that. Right. See, do it carefully. All right. That looks better, right? Right, now if I expand this out, so this is x squared times, right, because you remember, the key always keep in mind the next thing, you've got to integrate this damn thing, the square root of this damn thing. All right, so, all right, now that, if you then go, well, what's the integral of that? That's not one we've seen, is it? Right, but if you look at it long enough, what if I wrote it like that? Right? What you're hoping for here, as I keep saying with everything, remember, we know that a plus b all squared. Right, remember, that is true no matter what the hell A and B are. Doesn't matter, it's always true. So hopefully if you stare at that long enough, you will notice Yeah? Right, so look for this first when you do these ones with the square roots in them. Right, because then the next step is I need the square root of this. Now technically, when you take the square root of that, you should take plus minus. Right? But remember what we're doing, we're calculating the length of something. Right? So take the positive square root. If your answer turns out negative, all that means is, whoops, I should have taken the other one. Drop the minus sign, done. Right? That's all it means. Right, so just take this to be equal. Now that I can integrate. That's easy. Yeah? And as I say, if it turned out, right, because you're calculating the length of this function, if it turned out this was minus 4/3, all that's telling you is, oh crap, I should have taken the negative square root. That's all. Right? Instead of, imagine it's all multiplied by -1. Constants come along for the ride when you do integrals anyway, so it makes no freaking difference. Right? Just drop the minus sign. That's all it means. Right? Now, of course, if the square root doesn't magically disappear, then we need a substitution or an inverse trig substitution. But I would suggest that you always, with these ones, and obviously don't do it as badly as I did, right? But work this expression out first and see if you can write it as something all squared, right, to get rid of the square root, right? Because as I said, in general, integrals with square roots can be terrible things, right? And you remember that comic where one of the things says, "What the heck is a Bessel function?" Right? When you're doing integrals with square roots, often the answer involves Bessel functions, which is not something I expect you to know about at this stage. Right? But there's a couple more. There's a couple of examples in here. Right? But so define the length of this curve. Right? So I've got to integrate that. Obviously, there's nothing I can clean that up with, but that's a simple one. That's basically you're integrating root u. Right? Right? So I can do that simple substitution. What about this one? X squared minus an eighth log x. Right? Now, if I find its derivative, and I find this first, right, and I say get down to, ooh, I can't integrate the square root of that. That's not something I would expect you to do, right? But again, so what you look for here is this a plus b all squared, right? And hopefully, if you stare at it long enough, it is. Yeah? Remember, I'm not going to give you ones that you haven't seen before, right? So then I can do it, right? Then you just got to integrate the square root of this. Again, if this answer came out negative, all that means is you took the wrong square root. So very much just plugging things in. So the only thing to worry about with the Riemann integrate is the idea that it's like lots of little sums. That I'm never going to get you to do a Riemann integral from first principles, okay? All right, please have a go through, work through some of these examples. And in a few weeks, we're actually going to find a different way to calculate the lengths of curves that's equivalent to this. All right, but we'll leave it there for today. All right, don't forget to make sure you collect your test papers back from your practical class. If it's not there, or if there's any issues, come and see me in my consultation time on Wednesday. All right, I'll see everyone later.